today. Tony Feng has agreed to speak, and his title is Some Analogies Between Arithmetic and Topology. Okay, go ahead, Tony.
Okay, thanks a lot for the invitation to speak. So I'd like to start off by sort of contemplating solving some equation, say this one. This is my attempt to write down kind of random-ish degree 2g plus 1 polynomial. And I want to think about solving this, like finding the solutions to this equation and think about what they look like. And maybe the first thing to address is in what kind of number system are we talking about solving this equation? So, depending on sort of how you're trained, maybe your first instinct would be to solve this, for example, in the complex numbers. And so let me sort of plot what this looks like. This would then look like a one-dimensional complex manifold. So kind of two-dimensional topological thing. And when G is 0, it'll be kind of like a sphere. When G is 1, it'll be like a donut. When G is 2, it'll be like a two-hole donut, and so on. The experts will recognize that I've kind of added on certain points at infinity in a way that I've suppressed in order to get an answer which is compact. So technical things like this will continue to be done in invisible talk for the rest of the talk. So what we see here is that the topology of the space of solutions is kind of changing with G. And a more formal way to articulate this is to talk about the sizes of cohomology groups. So because this is a two-dimensional thing, it'll have kind of 3 cohomology groups that are non-zero. The H0 will be 1 in all cases. The H2 will also be 1-dimensional in all cases. And then this thing in the middle changes in an interesting way. So we get 0, 2, 4, and in general, 2G. Okay, so these cohomology groups are some way of attaching vector spaces to my topological space, which reflects the structure of the topology. Okay, so this is one answer to the question of what do the solutions look like. Now, if you're a number theorist, maybe you have in mind sort of other kinds of number systems in which you can contemplate solutions. For example, there's a field with p elements, or what is sometimes known as E mod p. This consists of numbers 0 through p minus 1, where addition and multiplication is as usual, except at the end you kind of have to reduce mod p or take the remainder mod p. And in this case, if you plot these solutions, there's not too much to say because there's only finitely many possibilities. There can only be finitely many solutions, and there's certainly no way to put like an interesting topology on them. We'll just see kind of discrete collective points, and so on. And a little bit more generally, you could contemplate. Well, it turns out there's a unique field with p to the n elements for any integer n. And so these are kind of the finite extensions of this field. And one can contemplate solving equations in these number systems, and you want to get sort of similar looking answers, just a discrete collection of points. So at first, it's a little disappointing that whereas we were looking at the complex numbers and we found sort of interesting topology and so on, this seems to be just kind of less interesting. There's less structure to this answer. But it turns out that there is structure which is manifested in a kind of subtler way. So I'm going to just refer to this equation from now on as being Z. And I'm going to write Z of fp to the n for the kind of solutions, the set of solutions. My equation in this fp to the n. And what turns out to be true is that kind of the number of solutions, so the size of this set, will be 1 plus p to the n minus the trace of the n power of some anamorphism on some 2D dimensional vector space. So the point here is that there's sort of one vector space and one endomorphism such that kind of its eigenvalues govern how many solutions you're going to see over all these finite extensions for every n. So this is some kind of hint that this counting process, counting solutions, although it has no topology, it knows about topology, kind of knows about 2D dimensional vector space. Okay, so I'd like to sort of flesh this out a little bit more in a way that looks more striking. So I'd like to recall that in the topological picture, when you have like a, let's say, N is a nice topological space, maybe even a manifold, with an endomorphism F, it has a finite number of fixed points, then the number of fixed points can be expressed as some sort of sum, trace on alternating sum, the trace of F on the homological side. Now, what's going on in this P situation? So let me explain one of the characteristic features of working on P. When P is 0, this P power map turns out to be additive. And that implies that on the space of solutions, inside the algebraic closure of Fp, which is kind of, formally speaking, a union of all these finite extensions, that there's a symmetry of the space, which sends out of x comma y to x to the p comma y to the p. That's because if this equation is satisfied, then its p power is satisfied, and then I can sort of distribute that p power over the addition operation. And I get that the same equation with this x and y raised to p power is satisfied. So that means that there's some kind of symmetry of this space, which is called the Frobenius. So continuing this story down here, is the case that the fixed points of the Frobenius on this algebraic closure of Fp is exactly the field Fp to the n. And that sort of implies that the fixed points of Frobenius to the n power on my solutions to my equation over the algebraic closure is exactly the solutions over Fp to the n. So I've managed to present this solution set that we're counting as the fixed points on something else. And according to this topological principle, at least, in the topological situation, you should be able to express that fixed point number as some kind of alternating trace on cohomology. And in fact, in this situation, sort of anticipated by Feng, Grothendieck, school defined sort of algebraic versions of cohomology groups called atal cohomology, which make this an analog of this formula true. So that this 1 plus p to the n minus this trace really becomes the trace of Frobenius on 0 plus the trace of Frobenius on H2 minus the trace of Frobenius on H1. So what we're seeing is something pretty striking, which is that, maybe I should say this kind of one-dimensional, and here's the 2D-dimensional thing as expected. So what's striking is that something which seemed to be a manifestation of topology when we consider our equation over the complex numbers does actually show up as well when we consider this context with no topology, the solving equations over finite fields. Are there any questions? I'd like to state this as a kind of general principle. That there's an analogy between sort of solutions to equations over FK bar, or more generally over algebraically closed fields and solutions.
Wait, I had a question.
Yep.
The formula you just erased when you wrote down, for about the number of fixed points of a map of a manifold.
Yeah.
I mean, you could have an isotopic map of say, the sphere that has many, many fixed points without changing the action on homology. Right?
Yeah, so this, okay.
Is that alternating sum?
So this formula I wrote holds under assumptions, and the fixed points are counted with a multiplicity. So when you account for those things, it kind of works out correctly.
Okay, gotcha.
There's an analogy between sort of solutions to equations over algebraic closed fields and over the complex numbers. And one expression of this analogy is that kind of, whereas here, these solutions will have some sort of topological structure, and one can write down homology groups. Here you can write down sort of atomic homology groups. And well, if you had a kind of n-dimensional space here, and complex dimensions would be, so say, sort of write it suggestively just like this. If you had an n-dimensional space here, it would have sort of n complex dimensions, and therefore 2 n real dimensions. And so, at least in our particular example, this homology was supported in degrees which are between 0 and 2, and in general, will be kind of 2 times the dimension. Complex dimension. And in this case, you would see the same behavior. So supported between 0 and 2 times the algebraic function. Another example of how these behave similarly is that here there's something called Poincare duality. Which says that HI is dual to H, the complex dimension minus I. And I guess, right, so again, I sort of assume these are compact, or maybe generally need to put compactly supported here. But the way this plays out in our example is that we have some space like this. And for example, we have, so this kind of represents classes of some dimension, codimension I. And the duality is just, the duality is given by some sort of intersection product. Given complementary dimension cycles, I can kind of intersect them and get numbers. And similarly, on this side, we will see Poincare duality for these homology groups. Okay, so now you might have noticed that I've been kind of particular about writing this subscript FP bar here. And what does that mean and is really necessary? So what it means is it's kind of declaring over which field I'm considering my equations. Because potentially, like in this example, it could make sense over sort of any field. And you have to sort of declare which one it's over. And this actually changes the answers for what these are. So it's certainly necessary. So maybe I give an example of what happens when you mess with that. So let's consider some sort of very degenerate equation. Let's just say something like, as an example, I just consider the equation like x equals 0. So I've got a variable x, and I'm just saying it's equal to 0. So on first reaction, it's kind of just like a single point, 0. But by what I've just said, you have to be kind of careful about declaring, like, over what number system are we considering this equation. So if we consider this over FP bar, then one way of saying that is we're going to call this spec FP bar. So in algebraic geometry, we're trained to think of commutative rings as any commutative ring as the ring of functions on some space. This is the space on which this FP bar is the ring of functions. And according to my analogy, this should be considered as being similar to the topological space, where you do the same thing with the complex numbers. So that's just a point. So maybe this will be this sort of topological analogy. Now I could just take this equation and consider it over something else. Like, let's suppose we said we're considering this equation over FP. So I'm going to represent that by calling this spec FP. I mean, it still looks like it's the same equation, but actually it turns out that this looks different, very different from this perspective of topology. And why is that? It's because it has lots of non-trivial covering spaces. So it cannot be as simple as a point. So there's this fact that there's a unique extension of FP of degree n for every integer n, every positive integer n. And kind of the union of all of those, or the universal cover, is FP bar. So I could analogously consider the exact same equation over all these intermediate things. And these all give in some way a non-trivial covering space over P, because there's sort of no map backwards. It's the way of drawing it. So whatever this is, topologically, it looks like a space which has a unique covering space of degree n for every positive n, and whose universal cover is like a point, or in other words, contractible. So there is such a space, and it's the circle. So this has a unique degree cover, which happens to be by the circle again, of degree n for every n, and then a universal cover is a kind of a real line, which is contractible. So from the perspective of topology, it kind of looks like a point. So, okay, here's a little picture. Maybe not too convincing, but it's meant to be kind of two-sheeted cover of the circle by a circle. Okay, so this is a kind of confusing point, but I hope that it's just something which needs to be emphasized going forward in the talk, is that when we have equations, we need to specify which field we consider them over, and certainly they behave quite differently from a topological perspective, whether we consider them over FP or something like FP bar. Generally, suppose we had some sort of more interesting equations, like the ones that we started off with. Then how would one get a feeling for what the topological analog was? So for example, you could take our Z that we started out with, and we sort of said that if we were contemplating this as an equation over the algebraic closure of FP, then it looks a lot like this kind of Riemann surface, or two-dimensional manifold. But if instead we declare ourselves to be interested in what it behaves like really over FP, then we're going to see a different answer. And one way to get at that is to say that considering this over FP is kind of giving a map to this kind of trivial equation over FP. And the intuition is that this is meant to behave like some sort of family or fibration in which these are the fibers. So this is meant to be analogous to a topological space, which lives over the analog of spec FP, which as I just said was sort of this circle, unit circle, and in particular a one manifold. And we are meant to sort of imagine that this thing looks like a sort of family of these curves all over this circle. So in particular, this is a two manifold, and therefore the total thing is kind of a three manifold. So that tells us that kind of this thing should have its atal homology, for example, behave like atal homology of three manifold. They'll have kind of support amplitude 3 and a Fourier duality of dimension. Are there any questions? So one can sort of push this analogy further. I've given you a recipe to sort of understand the topological picture of some equations, but certainly not all unless they're of interest. For example, in number theory, we would be really interested in solving equations with integers or rational numbers. And I haven't given you really a recipe to understand what that looks like. So I'm just going to say something brief about this, which is that there's an analogy of Feng in which one imagines this ring looking a lot like the ring of polynomials in one variable over T, or over FP, sorry. And so the rational numbers, which is the fraction field of integers, look like the field of rational functions in T. And this is now something which behaves a lot like Z. This is kind of a one-dimensional algebraic thing over FP. So whatever this is analogous to is again, by the same reason, a three manifold. Topologically, this looks like a three manifold. And so this is the beginning of a kind of interesting story, which was maybe introduced by Muser, wherein kind of number rings are now the three manifolds, and these primes, which are like little circles embedded in it, are now listed knots. And for example, it's true that the atal homology of something like this would have a sort of three-dimensional development. But I'm going to sort of go in a different direction than this story for the rest of the talk. Are there any questions about this? Okay, so I'm going to talk about something which is related to the arcade. A certain arcade parent. And so here, the centerpiece of the story would be some x, which would be a surface over FQ. Over FP. So this means a system of equations which kind of has two dimensions, or two, locally at least two free variables. And so whatever this is analogous to in topology, by using the same kind of reasoning, it's sort of like a picture like this, where you have one dimension circles worth of the base, kind of two complex dimensions or four real dimensions along the fibers. So this would be like a 5 manifold. And I'm going to discuss pairing on something called the Brauer of X. So let me say what the topological analog of this thing is before I actually do it. It's like if I took a 5 manifold, let's call it N, and I took homology degree 3, and I just for it. This is a finally generated abelian group. It has a free part and a torsion part taken for it. That's what you want to think of as the topological version of this graph. So are there any questions before I go further? All right, so let me just say that kind of formally one can define this in a very similar way. Well, it's a torsion group, and it's sort of, if I think of prime L not equal to P, and it's L power torsion. Let me put this in yellow. Could be thought of as H3X, H L, a little orientation character. But the reason why I put this in yellow is because this is slightly conditional. So it's sort of conjectural that this is a finite group that's equivalent to the BSD conjecture. And so it's a very hard conjecture. But what is true is that this maps to this unconditionally, and is supposed to be, this map is supposed to be an isomorphism. So for the purpose of this talk, I'm just going to sort of pretend that it is an isomorphism. But yeah, secretly, I'm assuming some kind of high-power conjecture to say this. Okay, so I'm going to define a certain duality on this object called the Artin-Tate pairing. And whatever it is, it has an analog on the topological side, which is called the linking form. Okay, so maybe I first sort of draw a picture illustrating like intuitively what it's supposed to be here, because I guess the formal definition of the big is not so intuitive. So I think actually it might be helpful to say, to sort of step back even a little bit further and mention that if M is a two-dimensional manifold, then it has a certain duality on its middle degree cohomology. Cohomology of M with integer coefficients, and I take the free part. This pairing like this, turns out that if you put in a ring for your coefficients, your cohomology is a ring, and so I can sort of multiply going inside this top degree. Then kind of part of the probability is that this is Z. So again, there's some invisible technical assumptions. You can fill in if you know what they are. So this is a perfect pairing by Poincaré duality. As to say, for even dimensional manifolds, I have a kind of perfect duality on the middle degree cohomology, the free part. So, of course, this doesn't work if n is odd dimensional, because then there is no middle. But it would be kind of unfair if odd dimensional manifolds didn't have any kind of duality. And it turns out they do, and that's what the linking form is. If n is 2n minus 1 dimensional, then there is a pairing, but it's not on, well, it's not on that, but it's on a torsion. So it's on HNM torsion. Take the middle and round it up. And so since these are torsion groups, they sort of have to be evaluated torsion domains. Okay, so there exists a perfect pairing. This is where the linking form is. And so first I'm just going to try to illustrate this with a picture. So let's say in this two-dimensional case, what this duality was supposed to be, well, just in a very simple example, when n is 1, we had one of these pictures on the board earlier, and it's given by a kind of intersection product on the one cycles, which are like loops in this space, and it is the intersection product. So given two loops in this two-dimensional space, you can intersect them to get a number. What is the analog of this picture here? So now let's give ourselves an odd manifold. Let's say a 3 manifold. This is the smallest dimension I can draw, which is interesting. And so in this kind of ambient 3 manifold, I would be considering degree 2 classes, or sort of in terms of cycles, they would be like one-dimensional cycles. So this time they don't intersect. But let's call this alpha and beta, and maybe I'll call it alpha n minus 1 because that's just mentioned beta n minus 1. Then the fact that these represent torsion classes implies that after I multiply alpha n sub n minus 1 by some integer m, then it becomes the boundary of something else of dimension n, topological dimension n. And so I can then intersect this other thing with this beta. The pairing of alpha beta would be kind of the intersection number between this alpha n and beta n minus 1. These are now a complementary dimension, except since I multiplied by m here, I kind of should renormalize this and divide. And in fact, there was some ambiguity of the choices, so that this, which is a priori a rational number, is really only well defined up to translation by some integer. So that's what this linking form is meant to be, something which measures, in some sense, the linking between two cycles which don't actually intersect. So if that wasn't very convincing, I'm going to give a kind of purely algebraic definition of this pairing. Okay, so I guess part of the formalism of homology is that you give yourself a map of groups, and then when you put these as coefficients, you get a map of homology groups with those coefficients. Okay, so I'm about to define this pairing linking form. And so furthermore, I can complete this story. This maps to 1, Z. And another sort of feature of cohomology is that one would automatically get kind of boundary maps from here to homology in the next degree. And one can sort of easily see in this case, if you know the formalism, that this map lands inside the torsion and is surjective onto it. So now if I had two classes, say alpha and beta in here, I could take one of them, say alpha, and write alpha equals boundary to alpha prime, where alpha prime is living in here. And then alpha prime and beta are kind of in complementary degrees. So alpha prime times beta is in H2n minus 1. M Q mod Z. And on-grid duality tells me that this is isomorphic to Q mod Z. And so this is a number, and I can define this to be the pairing of alpha and beta. And one can check that it's independent of choices and also a perfect duality. Okay, so that was all meant to be sort of a topological version of some duality which exists on this atypical homology of a surface over Fp. And to make it work in that latter situation, one just has to do appropriate binary replacements. So once we place our M by our X and put a little subscript atal everywhere, and sort of adjust the coefficients appropriately, then the whole story kind of applies verbatim, and you get the definition of this arithmetic pairing. So yeah, maybe specifically they consider this situation would use numbers for 2 and 3. Okay, are there any questions about this? So now I'm going to sort of shift towards stating kind of interesting questions about this. So it turns out to be not so difficult. This is using, so for odd manifolds, odd dimensional manifolds dimension congruent to 1 mod 4, this kind of linking form is skew symmetric. It turns out to be not difficult to show that this arithmetic pairing is skew symmetric. So the lemma is that arithmetic pairing is skew symmetric, which means if I take any alpha and beta, I pair them, and I consider the pairing in the opposite order, they add to 0. So there is something which is a little bit stronger than skew symmetric, which is alternating. We would say a pairing is alternating if alpha was 0 for all alpha. Okay, so if I were allowed to divide by 2, then these would be equivalent. I could take beta to be equal to alpha, twice beta 0. So if I could divide by 2, it's 0. But because of possible like 2 torsion, this one is a little bit stronger. Alternating is stronger. So take in his original paper on this, that was a 66 4x report, whether this was alternating, not just skew symmetric, and he conjectured the answer is yes. So one implication that this would have is this conjecture would imply that the size of this graph group is actually a perfect square. Because so I guess what I'm asserting is that there's just some algebra exercise that you have a finite abelian group with a perfect alternating form, and its size is a perfect square, analogous to how a symplectic vector space has that even dimension. So this conjecture went on to have a somewhat colorful history. Starting with computation of monin. So in the 70s, monin found an example of a surface X with the bar group being Z mod 2. And 2, well, it's not a perfect square. So that showed that the conjecture is wrong. Okay, so that was actually not that interesting, I guess. But it took a few more years when in 96, Frobenius found mistakes in this computation. And moreover, Frobenius was able to prove that, in fact, the size of the bar group is always a perfect square. At least the way compared to So in fact, we were sort of prematurely judging this thing. And in 05, Qingbu, Dino Lorenzini, and Michel Reynaud sort of showed that the size of our group is a square even in characteristic 2 extended states. So there's a certain technical complication being brushed under the rug again. For this, they need to assume that its bar group is finite, and then they show that it's a perfect square. Of course, we are kind of assuming it's finite, but in this case, and in the theorem which I'm going to present later, one can show some unconditional thing is perfect square, and then the conjecture is that that thing is the bar group. So maybe just to comment on these two proofs. I mean, it's kind of interesting to ask, like, how could you know something is a perfect square if you didn't know that there was an alternating pair? So in this case, Lon's observation was we have this skew symmetric form on G, but we don't quite need it to be alternating on all G to know that the size of G is a perfect square. It suffices to find kind of big enough, or in other words, co-isotropic subspace H containing its own annihilator such that the pairing is alternating when we just look at this quotient of H by H perfect. So it's still perfect here. If you could show that it was alternating here, then the size of this quotient would be a perfect square. And on the other hand, the kind of discrepancy between the size of this quotient and the size of G is symmetric because these two have the same index. So that's what he did. He found some small enough thing, or big enough thing, on which it was alternate. Whereas this proof is by completely different methods, by comparison. With another story in number theory, with sort of a story that comes up in the first 2010 diagonal conjecture. So they compare bar group with something called the K-char of some duality. And so perhaps you should credit some 2018 work of Geisser, who noticed that their comparison depends on a formula in 79 paper of Gordon, which is in fact wrong. And so it was kind of corrected by Geisser, and they show that in the end the correction factor is by another perfect square, so that the conclusion at least is true. That's
Their argument also would work in Enoch too, is that right?
yes, that's right. Okay, so finally, in my thesis, published this year, I proved that conjecture actually is correct, that the skew symmetric form is in fact alternating, at least if P is not 2. And sort of strictly speaking, the pairing was never really defined when P equals 2 on the 2 torsion part. So technically speaking, no conjecture was made when P equals 2. But I think like nowadays, it's expected that one could sort of define it and make this conjecture. But anyway, I say nothing about that. Okay, so in contrast to this kind of theorem, which is proved via techniques in arithmetic algebraic geometry, the proof of the conjecture ultimately depends on this analogy with topology, in particular on Steenrod operations. Key ingredient, Steenrod operations. So, in other words, it has a lot of inspiration from topology. Okay, so before I go on, are there any questions?
So why is there trouble with P equals 2?
With P equals 2, so basically it's, I had said that variable is some kind of analytic homology. When P is 2, if we're worried about sort of the 2 torsion, then we'll have to do kind of p-adic homology. And it wasn't, that theory wasn't really well developed at the time that R and K made this conjecture. Okay, so as I say, the proof sort of ultimately has inspiration from topology, and kind of in particular, it has some inspiration from study of the linking form. So since they have a theorem, I don't really know how to attribute this theorem, but anyway, what it says is that if n is a smooth manifold, then its linking form is alternating. Second default working class of its tangent bundle. So I'm going to explain this, but basically there's some way of producing a characteristic class mod 2 homology, and it's alternating if and only if this thing lies in the image of integral homology. The reduction map mod 2 from integral coefficient homology. Or in other words, if this class, which is a priori defined mod 2, lifts the characteristic 0. So here, Tn is the tangent bundle of n.
You assume M orient?
Yes, let's suppose maybe also connected. So this is the tangent bundle, which means it's some sort of family of vector spaces living over my manifold. For example, like circle with the usual smooth structure, assigns to each point the tangent space to the m at that point. And this W2 Tn, or maybe I'll just say more generally, this W2 is some function from vector bundles on n to the cohomology class n. And roughly speaking, it's trying to measure how non-trivial the bundle is. So if the cohomology class will vanish when this vector bundle has 2 independent segments, for example.
And one can even compute AA from this Deciphering necklace.
Compute what? Sorry.
Just intersection of something with itself.
Yes. There's, so implicitly, that thing is paired with some sort of Boxian of this class underlying this theorem. Okay. The reason why there's a question mark here is because it's maybe not super well known. In fact, I've never really met a person in the flesh who recognized the statement but and I certainly haven't found any literature, but some referee told me that this was a known thing. So, okay. But there's something not quite satisfying here because we were talking about the linking form, and that was an invariant purely of the topological structure of n. Whereas we've assumed here that n is smooth, and we've written down a condition which depends on the smoothness. This tangent bundle only makes sense because we have a smooth structure on n. So this is not quite ideal. We'd like a sort of purely topological condition here, and we'd like to not put a smooth assumption on n. So implicit in that is the idea that it should be possible to make sense of these Stiefel-Whitney classes when the Stiefel-Whitney class of a tangent bundle of m, even when m doesn't really have n, has no smooth structure. So that's what I'm going to explain next, and that's where these Steenrod operations come in. So how the story goes is that this cohomology ring of n with monotone coefficients, well, first of all, it's a ring in which 2 is 0. So as we have been discussing, it has a Frobenius. Or very concretely, in this case, we just take that element squared, and that happens to be a linear map because 2 is 0 this ring. So this is the map of I, H. We're going to call it square upper I in this case. Now, this is not just any ring in characteristic 2, but one which arises by kind of a very particular process, in particular by a sort of process which involves derived or homotopy theoretic operations. And it turns out that that leads to sort of derived or homotopy theoretic shadows of the squaring map, which look like they go from hi to ai plus j. We call this square j. And you have such maps when j is less than or equal to I is 0. Okay, so so there's an interpretation of how to come up with these things based on sort of failure of this homotopy commutative multiplication to come from an actual commutative multiplication. Maybe I'll just say something quick to give you an idea of that. But yeah, I guess let's just do an example when j is I minus 1. I want to sort of give some idea of what this thing is. And the point is that this arises, as I said, as this kind of homotopy class or equivalence class of objects. So it's a quotient of Ci by some sort of boundary operation, co-cycles, co-boundaries. And the multiplication on this group does come from multiplication up here, but although it is commutative here, it is not commutative before passing this quotient, which means that if you had two classes, u and v and this zi's, then uv minus vu is not necessarily 0, but it is the boundary of something else. And what Steenrod did was construct these sort of higher multiplications or higher cup products, such that in this case, the cup 1 product of u and v is some explicit thing whose boundary is this, witnessing the fact that this becomes 0 in this quotient. And if you take u to be equal to v, then what you find is that then this is 0 for obvious reasons. And so this u times v, cup 1, u cup 1v, is actually itself a co-cycle degree 2i minus 1. So a priori this isn't c2i minus 1, but this, in the case where they're equal, it's even z2i minus 1. And then it gives you a cohomology class. So the next sort of Steenrod square of class represented by u is exactly this u cup 1u. So anyway, what's the relevance of this to our story? So we have these maps from the top dimension cohomology of m minus I the top homology dimension of M. So again, assuming M is closed, oriented, and connected, and saying we have these things which could be interpreted as linear functionals on this degree of homology. And concrete duality then tells you that this map has to agree with, has to be given by multiplication by some unique element bi. And the theorem of Wu is that if M is smooth, then there exists a kind of explicit universal tangent basis matrix taking these classes bi to the wi's of the tangent bundle. So take some examples. So B1 is W1, B2 is W2 plus W1 squared, so on. So explicit means we could easily write them down. Universal means they don't depend in any way on M. And tangent basis means that this transformation is invertible. In fact, it is always a triangular kind of tangent basis. And what this means is, well, this substance is an answer to our question. These VIs are defined by purely topological operations. And so they don't depend on any kind of smooth structure. And so this thing can't depend on any kind of smooth structure. And in fact, this gives a way to kind of define the C-ordering class of the tangent bundle even when M isn't smooth. So it has no tangent bundle. Namely, I would just take this tangent basis and apply it to the VIs and call those WIs of TM. So one can in fact prove this theorem and prove this theorem. We can forget that this is smooth. And we can put this in quotes, where it means define it in the above way. And this is true, that the linking form is alternating if and only if this newly defined characters class lifts the characteristics zero.
You need quantity duality. So what do you assume in that?
Well, I still assume that it's closed oriented and connected.
So just topological manifold.
Just topological manifold, yeah. No. Point is, I remove the smooth structure. But certainly one can find counterexamples in topology where this doesn't hold, this doesn't hold. So kind of the final question is, oh, so maybe I should also say, plus you can prove version for a polynomial answer, which would apply to problem at hand. Takes question about priority. But what's sort of strange is that a condition which sort of clearly isn't always satisfied in topology somehow is always satisfied for these five-dimensional Poincare duality spaces which come from surfaces over finite fields. And so since I don't have much time, let me just leave you with a picture that was a useful heuristic, proving kind of why every surface over FP is satisfied with the analog of this condition. So when we were writing down kind of what topological space does this look like, we didn't say it looks like any phi manifold. We said it looks specifically like one that has the following kind of structure. It's a phi manifold which has some kind of vibration over the unit circle and whose fibers are, well, they're analogs of this, so they're analogs of complex surfaces. And the point here is that this phi manifold is built out of two pieces, both of which kind of evidently satisfy the thing that they need to. So for complex manifolds, it's sort of easy to check that this kind of condition would always be satisfied. There's even a distinguished choice of lift given by term classes, and the tangent bundle of the circle is trivial, so that it also doesn't really interfere with this kind of condition. And so, as I say, that's a heuristic for the proof of the conjecture in this algebraic case. So I'll stop there. Thanks for your time.
Beautiful. Thank you very much. I guess we have some time for some questions.
in the topological case, is it this vanishing for any things favoring over the circle of dimension 4?
If this thing also satisfies this condition, this four-dimensional thing, then it would be okay, yeah, in topology as well.
Oh, so you use that there is a complex structure.
Yeah, yeah. I use yeah. So, and in the algebraic case, what I use the fact that some sort of appropriately defined Steenrod class has a lift because the lift can be chosen to be like a Chern class.
Do you need existence of complex structure just on one fiber in the topological case, or there is some compatibility having some complex structure on the relative tangent bundle?
I guess I'd say that I'm thinking about it on the relative tangent bundle, but yeah, I don't really have anything stronger to say about than this. So I know that complex manifold vibrations satisfy this, so it's okay, but I haven't sort of thought about specific families, like what exactly satisfies the condition.
Are there any other questions?
I have a small question. Could you try to, in the case where it's not a smooth, could you try to define like the unit circle bundle of the tangent bundle anyway by taking sort of a small neighborhood of the diagonal, so to speak, in some kind of limiting sense, removing the diagonal and protecting that down?
That won't produce exactly the right answer. That's sort of how this with theorem is proved.
Great. Well, I'd like to thank the speaker again for extremely interesting talk. Thank you very much.